So pH is a hugely important number, and you absolutely need to know the definition of it, which is that. So there are all sorts of calculations which revolve around that, so you've got to make sure you know the definition, and you've also got to make sure that you can work with it on your calculator. It's usually just written as log, but you need to be clear that that is log to the base 10. It's not the same as that which we used, for example, when we did the Arrhenius equation and things like that. That's the natural log. This is log to the base 10, which is usually just written as log on your calculator. If you're not very familiar with logs, it doesn't really matter, because all you actually need to be able to do is to make it work on your calculator, but it is just kind of vaguely worth sort of having a feeling for what logs are, just because it helps you make sense of how this scale works. So the log of a number is the power to which you have to raise 10 in order to reach that number. So for example, log to the base 10 of 100 is 2, because 10 to the 2 is equal to 100. And so log to the base 10 of 1,000,000 is 6, because 10 to the 6 is 1,000,000. And log to the base 10 of 0.1 is -1, because 10 to the -1, which is 1 over x, which is 1 over 10, is equal to 0.1. So that's the idea of a log. Obviously, for numbers which aren't actual multiples of 10, then that's why you get fractional numbers, and we won't get into the maths of that. But this gives you an idea of the sort of range of these numbers. And you're used to the idea that the pH scale goes roughly sort of 0 to 14. As we'll see, those are not fixed limits, and you can go outside them. But just to get an idea of that, what that means is 0 to 10 to the 0 is equal to 1. In other words, the log of 1 is 0, and the log of 14 is 10 to the power 14. So that means that those numbers are 14 orders of magnitude apart. And what that gives you an idea of is that this pH scale is able to deal with hydrogen ion concentrations which are 14 orders of magnitude different. In other words, 100,000 billion times different. So if we're going to get used to using the pH scale, the simplest place to start is with strong acids. So remember the definition, first of all, of a strong acid is that it's completely ionized in aqueous solution. And that makes life very simple, because, for example, if we take nitric acid or hydrochloric acid, those are the two common acids which you need to know are strong acids. And what it means about them being strong is that they ionize completely in aqueous solution. So every single molecule virtually, I mean, it's a bit of an approximation, but it's a pretty good one really, every single molecule breaks up to give you H plus and NO3 minus, or H plus and Cl minus. That's what it means when we say they're strong acids. And of course that makes calculations very easy, because if we have, say, 0.64 moles per dm cubed HCl, it means that the concentration of H plus is simply 0.64 moles per dm cubed, because each HCl molecule breaks up, and however many of those you'll get that number of H pluses. So that makes the calculations very easy. So we can see how the pHs are then going to work if we just take, first of all, some nice round numbers. If we have 1 mole per dm cubed HCl, that means that the H plus concentration is 1 mole per dm cubed. And minus log of 1, well, log of 1 is 0, and minus 0 is still 0, so the pH is 0. Okay, so that number, which we think of as the sort of somewhere around the bottom end of the pH scale, corresponds to a 1 mole per dm cubed concentration of H+. If we had 10 moles per dm cubed, which is approximately the concentration of concentrated hydrochloric acid, then log of 10 is 1, and minus log of 10 is therefore minus 1. So actually, you can have negative pHs. There's no problem with that. You don't come across them very often because we don't tend to talk about the pHs of these very concentrated solutions. We tend to just talk about the concentration, but it's a perfectly real thing, and so don't be frightened if you get negative pHs like that. If we take something more simple like 0.1 moles per dm cubed, which is the sort of number you get in titrations typically, that sort of range, well, log of 0.1 is minus 1, and so minus of minus 1 is plus 1. So the pH is 1 for a 0.1 mole per dm cubed solution, and 0.01 moles per dm cubed gives you a pH of 2, because the log of 0.01 is minus 2, so minus the log is plus 2. So you can see the way it works. Each time we increase the concentration by a power of 10, the pH drops by 1 unit. And that's the way the pH scale works. So for numbers which are not round multiples of 10 like that, you need to use your calculator, obviously, to get what the pH is. So the important thing is just to try it and make sure that you and your calculator understand one another. So let's take, for example, an H plus concentration of 0.7 moles per dm cubed. And just try it on your calculator, see what you come up with, and what you should find is that the pH is 0.155. So if you get that, when you put minus log of 0.7 in there, then that's good. If you don't, you've got to play around, make sure that you figure out how to get your calculator to give you the right answer. If we take another example, so let's say 2.3 times 10 to the minus 4 moles per dm cubed, so a much lower concentration this time. Again, plug that into your calculator, minus log of that number, see what you get, and you should find its pH is 3.64. Okay, so the pH is a lot higher, corresponding to the fact that the concentration of H plus is a lot lower. Now, of course, you need to be able to go the other way as well. In other words, if you're told what the pH is, you need to be able to turn that into an H plus concentration. So that means we've got to be able to rewrite this expression in the sort of inverse direction. And the way it works is that H plus concentration is obviously the inverse log of minus the pH. And the inverse of log to the base 10 is just 10 to the power x. So in other words, that's equal to 10 to the power minus the pH. And on most people's calculators, the inverse log function is actually written as 10 to the x. Okay, so you've got to do 10 to the power minus the pH. So again, the thing to do is try it with some numbers on your calculator and see what you get. So let's say the pH is 1.8. So get your calculator, try plugging that into it. Usually the inverse log function is the most efficient way to do that. Obviously you could do it as 10 to the power like that, and that would also give you the same number, but usually the inverse of the log function takes you directly to that, which just saves you a few keystrokes. So try pH is 1.8. That means that H plus is equal to 10 to the power minus 1.8. And if you try that, you should get 0.0158 moles per dm cubed. Try another one. So 6.7, for example. So much higher pH, so you're going to expect the H plus concentration to be much lower. And if you plug that in, 10 to the minus 6.7, 2 times 10 to the minus 7 moles per dm cubed. 2 times 10 to the minus 7 moles per dm cubed, which is, as we expected, a much smaller number. So if strong acids were all we had to deal with, the pH scale, once you're used to it, would be very straightforward. But actually, strong acids are sort of the least interesting of the things that we have to deal with in terms of pHs. So they're very much our starting point. But then, having got to grips with the function, we can then start to look at more interesting applications.